Tonight, on The Sky at Night, we're doing things a bit differently.
Over the years on this programme, we have investigated all sorts of mysteries. From sinister black holes lurking in galaxies, to sudden shocks from the early universe.
The night sky we all look at is hiding secrets, only telling us part of the story. And so tonight, we're going looking for cosmic ghouls lurking in the shadows.
And where better place to do that than here, in Provan Hall, Glasgow's own medieval and haunted building, where strange things have supposedly been seen, like a man with a dagger, or spooky faces at windows, or even the ghost of King James V himself.
We'll take the most sophisticated equipment that the Sky at Night budget can afford and stalk the corridors of Provan Hall to see what can be found.
For mysterious voices of the past, with stories to tell from the darkest parts of the universe.
To a cosmic ghoul that's still haunting astronomers decades after it first made its presence felt. And so tonight,
we're going ghost hunting.
Cosmic ghost hunting.
Welcome to The Sky at Night. The building behind us is supposedly one of the most haunted locations in Scotland, Provan Hall House.
And we're told that it harbours several ghosts from its 550-year history.
So, shall we take a look inside, Chris? Unless you're scared.
Not scared. Ghosts aren't real.
To find out what's lurking inside Provan Hall, we need to look beyond what our eyes can see. So I'm going to be listening out for unusual sounds while Chris searches for strange movements with a thermal camera. See you on the other side.
Any luck? Of course, we're a science programme, so it's not ghosts we're after, but finding new ways of sensing what surrounds us in the cosmos is a large part of the modern astronomer's job. Take this infrared camera. Paranormal enthusiasts believe it can show them supernatural shadows, but actually, it's just detecting light at a wavelength longer than our eyes can see. Our vision is confined to radiation in a small part of the electromagnetic spectrum, the part we call visible light. But celestial objects give off light in other parts of this spectrum, like ultraviolet and infrared. Hang on, what's this?
Hi, Chris.
Hiya, how are you? Of course, I haven't found a ghost. I found an astronomer. Dr. Olivia Jones from the UK Astronomy Technology Centre, who's recently played a key role in solving a mystery about an exploding star, known as a supernova. So, you've been looking at a particular supernova. Tell us about it.
We've been looking at supernova 1987A, which is a supernova that went off in the year 1987. It was the first time we really got to see the physics of a star going boom.
When stars explode, their cores collapse. For more massive stars, this will create a black hole. But cores of stars like the one that produced supernova 1987A should collapse into an extremely dense ball of neutrons, a neutron star.
The mystery is, we knew a neutron star was meant to have formed, and we went looking. This is the densest material you can find in the universe. A small teaspoon of this weighs as much as Everest. We looked in the optical, we went looking in the ultraviolet, in the radio, and we saw nothing. The best telescopes in the world, and we couldn't find this neutron star.
A missing neutron star would have meant our theories about how stars die were wrong. So Olivia and her team were very keen to find it. But there was one thing in their way: dust.
What you have right in the core of 87A is a big pile of dust. It hides everything from optical light, it hides all the energetic UV light. Anything that emits at very short wavelengths is absorbed by the dust, and so you can't see through it.
But the new James Webb Space Telescope, or JWST, offers something that other telescopes didn't. It can detect longer, infrared wavelengths in unprecedented detail. So Olivia and her team pointed it at supernova 1987A as soon as they could. This is where JWST comes in.
Yes, JWST is an infrared telescope, and it lets you unveil and peel back all those layers you can see right into the core.
So why is the infrared important here?
The infrared is great because it lets you see through material. We've got an infrared camera here. I picked this up, and there's a handy sheet nearby.
Oh yes, very good.
If you look with this, with the infrared camera, you can see my hand.
Oh yeah, really clearly. And of course I can't with visible light, so the infrared's able to travel through the sheet.
Yes, the longer wavelength of infrared light lets you see through material better.
So if your hand was the centre of 1987A, the sheet was the dust, and that was James Webb, this is exactly what we're doing.
Yes, and the really good news is we found the neutron star, which I think is a relief, because if the neutron star wasn't there, we would have really had to change physics.
Using data from JWST, Olivia's team were able to find the signatures of a neutron star at the centre of 87A. A 37-year-old cosmic mystery finally solved. Well, it's a thrilling discovery about a fabulous object, and keep an eye on it for us.
We will do.
For me, finding a neutron star is far more exciting, wondrous, and, likely than finding a ghost. But is a neutron star not a type of cosmic ghost? A once bright star, still haunting the universe long after it ceased to shine?
While infrared telescopes allow us to detect parts of the electromagnetic spectrum that we can't see with our eyes, we suspect there's a huge part of our universe that can't be detected by any part of this spectrum. We call this the dark universe. Everything that we can see, the planets, the stars, the galaxies, they make up just 5% of the universe. The question is, why do we think that there's missing stuff out there?
I just got hooked on watching the stars.
A voice from the past is going to help me answer that question.
Got more interested in watching the stars.
Vera Rubin, a pioneer in the study of the dark universe.
So I went to the library, read books, built a little telescope, and just decided I wanted to be an astronomer. I had a physics professor in high school who didn't really know how to relate to a young girl who was interested in science. When I finally went up to him and told him I was going to college on a scholarship, he said, well, you should do all right as long as you stay away from science.
In 1948, despite that atrocious advice, this woman, Vera Cooper, graduated from Vassar College. She was the only astronomy major in her year, and she was primed and ready to find out more about the universe. She went on to earn a master's degree and a PhD. She married and changed her name to Vera Rubin and became a full-time astronomer. As a woman in astronomy, Vera continued to experience inequalities, but it didn't deter her. She was denied access to the Palomar Observatory telescope. They said they had no ladies' bathrooms. So she cut out a skirt-shaped piece of paper, put it over the male figure on the bathroom door, and said, there you go, you've got a ladies. Some years later, she made an astounding discovery. While researching the motion of spiral galaxies, Vera found something that didn't add up.
In a galaxy, it looks like most of the light is at the center, and therefore we had expected that most of the mass would be at the center. And just like in the solar system, where most of the mass is at the sun, you expect that as things get farther and farther away, they orbit more slowly. And what we found is that these stars are going just as rapidly as those stars, and we're forced to conclude that they're responding to a gravitational field we don't see. And that gravitational field must be composed of dark matter.
Many astronomers were reluctant to accept this conclusion, but Vera persevered. She got data from more and more of these spiral galaxies and found the same result every time. Each one needed to have a lot more matter than she could see to move the way they did. Eventually, the astronomy community could deny it no longer. The galaxies and the universe contained unseen matter, dark matter. Sadly, we lost Vera in 2016, but in many ways, her legacy lives on. On top of her pioneering research into the dark matter contained in galaxies, Vera was also a fierce advocate for women in science. She was a tireless trailblazer for astronomers working with children, as a working mother of 4 herself. And her memory also lives on through a groundbreaking new observatory named after her. The Vera C. Rubin Observatory has the largest camera ever built for astronomy. It will help us answer some of the biggest questions about the universe, with a key goal at understanding the nature of dark matter. It might not be ready to take data quite yet, but the observatory's new camera has already taken this image of the team that are working on it. And all those people will be following in the footsteps of the smart, the daring, the tenacious, the wonderful Vera Rubin.
What we all dream of is that when you do when you ask questions in science, when you ask questions of nature, you will get answers that are much bigger than what you went out to find.
Analysing the movements of stars and galaxies has provided evidence that dark matter exists. But how do we actually go about finding it? Dark matter expert Professor Chamkaur Garg is going deep underground in Yorkshire to find out how UK scientists have been searching for elusive, ghostly dark matter particles.
Over a kilometre beneath me is one of the most incredible labs in the UK, the Bolby Underground Laboratory. And deep in this working salt and polyhalite mine, scientists are trying to detect particles that have just passed through the ground completely undisturbed, like ghosts moving through walls.
In the 1990s, scientists realised that Bolby was a perfect location for conducting research into dark matter.
Okay, good to go.
This far underground, cosmic radiation is reduced by a factor of 1 million, making it easier to spot particles that normally pass through undetected.
Good evening. I'm in a most unusual setting.
Patrick Moore and the Sky at Night team also visited Bolby 20 years ago, but back then the lab was a much smaller operation.
Here I am in a lift going 3/4 of a mile underground in Bolby Mine toward this strange observatory.
One thing that hasn't changed in the last 20 years is a 7-minute lift ride down into the mine.
So we've just got into the cage. We're still up on the surface, but we've just started moving now. The next time we get out of this, we'll be deep in the earth.
Bolby is now the site of a vast range of groundbreaking research beyond dark matter, including astrobiology studies into deep subsurface microbial life, testing of planetary rovers, and other technology developments for planetary exploration. But I'm really here for those ghostly particles, just like Patrick in 2004.
What experiments have you got running down here?
The Zeppelin detector behind you is a liquid xenon detector.
This detector, called Zeppelin, was looking for theoretical dark matter particles called WIMPs, weakly interacting massive particles. It contained liquid xenon, which is great for detecting radiation because it gives off flashes of light when particles collide with it. The hope was, if this liquid xenon was brought underground where most other radiation from space couldn't reach, it would be possible to pick out a collision between a xenon particle and a WIMP. And although Zeppelin didn't find a dark matter particle, that liquid xenon technology went on to be used in dark matter detectors around the world, including an experiment called Lux Zeppelin, or LZ, currently the world's most sensitive dark matter detector. I'm meeting facility manager Emma Meehan to learn more.
So can you tell us about how you found yourself at Bolby? It's an amazing story.
Yeah. I had a friend who worked here who called me and said, does your mum want a job? It's 2 days a week coming underground to clean in this underground lab. I said, my mum won't work in the mine, but tell me about it, maybe I can take it. And then I got the job, and at lunch breaks, we would sit down and I would sit with all of the academics and we would start to have chats about physics. So I started to learn. I decided to study with the Open University, and I started to kind of throw myself in the way of scientists saying, what are you doing? Can I help you do this?
In just 8 years, Emma went from cleaning the lab 2 days a week to being their senior science technician. She also helped to develop this lab, BUGS, which has a key role to play in the search for dark matter.
BUGS stands for Bolby Underground Screening, and what that means is that we look at materials here in terms of their radioactive content. Every little bit of radiation can swamp the detector with noise. So when we're building these detectors, we care about the materials that we build them out of. We want to check how radioactive they are.
There's the LZ experiment that's operating right now, and these detectors played a pretty important part in that, right? What
Yes.
were they doing?
So we screened an awful lot of the electronic eyes, the photomultiplier tubes.
These electronic eyes are extremely important. They are the part of the detector that will confirm that a dark matter particle has passed through the liquid xenon.
What we know, Cham, is that we're never going to see the dark matter particle. We're only ever going to see its interaction. And what that would look like in the terms of this liquid xenon is that the particle would pass through, it would hit a nucleus of the liquid xenon, which would recoil. Dark matter will disappear off, gone. But that recoil will create a lovely flash of light in that xenon. But these photons are picked up by these incredibly sensitive electronic eyes.
If a detection is made, it would transform our understanding of the cosmos. And it would be a very special moment for Emma.
So if dark matter is detected in LZ, what I know, Cham, is that I held the thing that is going to see dark matter for the first time.
But even if dark matter is not found at LZ, the search for these elusive particles will not stop there. The BUGS lab is now being used to screen possible materials for use in a new, bigger, more sensitive detector called XLZD.
So you'll be screening materials and shipping them where? Where's XLZD?
Well, what we know is that there is only a very few places in the world where it could be, and here at Bolby is a strong contender as one of those.
Well, thank you so much, Emma. It's been great to learn more about what's going on here and all the work that you and everyone here at Bolby have been doing.
Thanks, Cham.
Even as someone who's worked on dark matter for most of their life, I'm still awestruck by the work that goes on down here at Bolby Mine. And it's easy to question why we'd spend so long and so much effort looking for something that we can't even see. But it's mind-blowing to think that with just a few pings in a xenon detector, we could understand one of the greatest mysteries in the universe. And I, for one, am looking forward to a ping.
Mysterious dark matter is enough to give astronomers nightmares. But black holes are the true monsters of the cosmos, hidden out there in the dark. And in the past decade, scientists have found a clever new way to track them down.
Light. It's how we see everything around us. It's how we find our way, how we notice the people we love, and how we recognize ourselves in the mirror.
But just as there are other ways for us to comprehend the universe around us, like hearing, listening to sound waves, There are other types of information that we can pick up from the universe, like gravitational waves, ripples in the fabric of space itself, which can reveal cosmic events that otherwise we'd never be able to see.
Oh, Tessa, there you are. How are you?
Good, thank you.
Professor Tessa Baker from the University of Portsmouth's Institute of Cosmology and Gravitation is at Provan Hall to tell me more.
One of the most exciting things is that we no longer just need to look at the universe in light. We can use other methods. So tell us what you've been up to with gravitational waves.
So we have a network of detectors all over the Earth, and these work together to detect gravitational waves, these tiny, tiny ripples from merging black holes and exotic stars.
Most of the time, gravitational waves are too small to be detectable. But when two dense objects like black holes or neutron stars merge, they send gravitational shock waves out across the universe.
We get these ripples, these gravitational waves spreading out through the universe. How on earth do you detect them?
You need a gravitational wave detector. And that's made of two really long laser beams. Our current ones are about 4 kilometers long, and they meet at right angles. When a wave comes through, it will change the lengths of those two arms. So it'll make one a little bit shorter and make one a little bit longer. And when we bring those laser beams back together, we can tell that's happened.
But the change is really small, right?
Yeah, absolutely. Yeah. Smaller than the size of an atom.
The properties of the gravitational waves we detect, their durations and frequencies, tell us about the speed and mass of those merging black holes and neutron stars. And it's possible to bring those properties to life through sound.
So one of the cool things about gravitational waves is we can actually convert them into audio files that you can hear.
Okay.
So let's show some examples of this. And I should stress, gravitational waves don't actually make a sound, but it's just like converting radio waves into sound.
Okay.
So here is the first gravitational wave we ever detected.
Okay, I can hear that. I was expecting something a bit more spectacular, I have to say.
So it's very short, right? And it's at a pitch which is quite hard for the human ear to hear.
And that's just because things are happening fast, right? These black holes are spiraling around each other really quickly.
Yeah. But remember, we said that neutron stars can also merge and make gravitational waves.
Right.
And because they're lighter, they produce an even stranger sound. So here is the sound of that binary neutron star event we detected in 2017.
Well, it's a proper whoop at the end.
Right, the sound is much longer. And again, that's just to do with the neutron stars being lighter, so they're in the sensitive range of the detectors for longer.
So you do hear it for longer?
Yeah.
These gravitational waves are already revealing unseen parts of the universe. But to learn more, we need to detect new types of events that produce waves of different wavelengths. For that, we need new detectors. And there's one particularly ambitious project, the Laser Interferometer Space Antenna, or LISA, which is taking gravitational wave detection into space.
Tell us a bit about LISA and what it's going to see that we can't see otherwise.
So LISA is going to be a triangle of detectors in space. So these 3 detectors fly around and they have laser beams between them. So it's like what we have on the ground, but all in space without supporting infrastructure.
I'm presuming they're quite a long way apart as well.
2.5 million kilometers.
Oh, wow, okay.
Huge. And the reason we want the arms to be that long is that allows us to pick up gravitational waves that have really long wavelengths. So at the moment, we're seeing things that are 10, 20 times the mass of the sun. These black holes that LISA will pick up are maybe 1 million to 100 million times the mass of the sun.
So they're the ones that live in the middle of galaxies, right?
Right.
It's going to be so exciting. I know we've got to wait and you're keeping us entertained in the meantime, but thank you very much for telling us about gravitational waves. Come back soon.
Thanks, Chris.
Hearing those sounds produced by ripples in space-time is kind of breathtaking. Gravitational waves allow us to access this unseen but really important part of our universe, cosmic events on the grandest of scales detected down here by the tiniest change in the movement of light hitting a mirror. Now, Pete is at the Bedford School Observatory to tell us how to spot another hidden object in the night sky.
We're all used to looking at bright objects in the night sky. Moons, planets, stars, comets, meteors. But the absence of light can also help reveal some rather ghostly-looking objects, which are known as dark nebulae.
Dark nebulae are interstellar clouds that are so cold and full of dust that they block out all visible light. These spooky black clouds are important spawning grounds for new stars and planets.
So with dark nebulae, there's something for everyone, whether you have an observatory like this, or whether you're just outside looking up at the night sky without any equipment.
As the skies start to darken after the June solstice, it's a good time to start looking for dark nebulae. One prime location is near the constellation Aquila the Eagle. First, identify the large prominent asterism known as the Summer Triangle, made up of the stars Deneb in Cygnus, Vega in Lyra, and Altair in Aquila. Just northwest of Altair are two dark nebulae silhouetted against the rich background star field. Together, they look like a capital E and are known as Barnard's E after Edward Emerson Barnard, a gifted observational astronomer who compiled a catalogue of dark nebulae. Other summer examples include the Pipe Nebula in Ophiuchus, to the east of the bright red supergiant star Antares in Scorpius. Another smaller example sits near the bowl of the Pipe and is known as the Snake Nebula. If you live in a dark sky region and can see the Milky Way passing through Cygnus, with just your eyes, look out for where it splits due to a region of dark gas and dust. This is the Cygnus Rift, and the region to the north of it, near the bright star Deneb, is a dark nebula known as the Northern Coal Sack.
To get a good image of a dark nebula, you need relatively dark skies, so probably best to wait for the effects of the June solstice to wear off, and also to have the moon out of the way. A mid or wide-angle lens is good for capturing large areas of the Milky Way, which will show bright star fields and dark dust lanes. As ever, if you get any photos, we'd love to see them, so do upload them to the Sky at Night Flickr. Now, there was an amazing display of the Northern Lights, which was visible across the UK in early May, and Sky at Night viewers got some incredible photos.
When you're looking out for all those amazing objects in the night sky, don't forget to think about those that you can't see.
Because in the galaxies, the dust and the darkness, cosmic ghosts are lurking.
Each with an incredible story to tell us about our universe. Good night.
Good night.
Brian Cox and Robin Ince are back with a witty look at the world through scientists' eyes. The new series of the Infinite Monkey Cage podcast. Listen now on BBC Sounds.